Hi, everybody. Now we're going to talk about normal subgroups and factor groups. This is a way of building new groups out of old. We saw already that you can take two groups and combine them to make a product group. Factor groups are a little bit different. They sort of start with a big group and make it smaller by kind of dividing out the action of a smaller group. This will take some explaining, so don't worry if that didn't make a lot of sense. But in order to talk about the idea of a factor group, we need the crucial idea of a normal subgroup. And so the first thing that we're going to talk about is normal subgroups. This may seem a little unmotivated, but once we talk about factor groups, the reason for having the definition of normal subgroups will become clear. So let's start with the definition. So a subgroup is called normal if it has the same left cosets and right cosets. So if the left cosets of the group H and the right cosets of H are the same. That is to say, H is normal if for all G and G, the coset GH is equal to the coset HG. And let me just remind you that the coset GH is what you get if you take every element in H and multiply it on the left by G. And the coset HG is what you get if you take every element in H and you multiply it on the right by G. This should be H and H. G is fixed. So a subgroup is normal if these two sets of cosets are the same. Now, an equivalent way to check if a subgroup is normal is to consider the set GHG inverse, which is the collection of elements that you get if you your G is fixed, and you take all the elements of the subgroup H and you multiply GHG inverse for each element of H. And if that gives you H back, then your subgroup is normal. And so let's just quickly look at why these two things are the same. And so what does it mean? Let's first assume that GHG inverse equals H. So this means that any H in H can be written GH prime G inverse, and that's because H is contained in GHG inverse. So that means any H in here can be written in the form GH prime G inverse, which tells you that you're in here. And similarly, any GHG inverse is in H. That's the assertion that GHG inverse is contained in H. And these two things together say that the sets are equal. So let's compare, we want to show that GH equals HG. And as usual, we have to show that GH is contained in HG. And what does that mean? Well, that means that if I take X in GH, that means that X is equal to GH for some H and H. And we use the fact now that if we write X G inverse, which is equal to GHG inverse, this is in H. Because we've just said that GHG inverse and H are the same. So let's call that H prime, and we get that XG inverse equals H prime. And then you see we have that X is equal to H prime G, which implies that X is an element of HG. So we were able to move the G to the other side, is one way to think about it, at the cost of changing H to H prime. And if we also want to show that HG is contained in GH, you do exactly the same thing, but kind of in the other direction. So maybe I won't write that out. But the argument for HG contained in GH is symmetric. On the other hand, suppose GH equals HG. Well, if I take H in H, then I take H in H, then I know that GH can be written as H prime G for some H prime. Because the set GH is the same as the set HG, and that means that GHG inverse is equal to H prime, which is in H. So what I've shown here is that GH, if I look at, so this tells me that GHG inverse for any H in H belongs to H. And again, that tells you that GHG inverse is contained in H. And if you want to go the other direction, you can give a symmetric argument, or you can use G inverse instead of G and just reverse it. So again, I won't belabor this, but the reverse argument to show that H is contained in GHG inverse is symmetrical. So these two notions of being a normal subgroup are the same. Now let's look at some examples. So the first and kind of simplest example, and maybe one of the reasons why the idea of a normal subgroup seems unfamiliar, is because every subgroup of an abelian group is automatically normal. And so if you were used to working with abelian things, you don't have to worry about normality. Everything is normal. And the reason for this is that, so suppose we have an abelian group G, and H is a subgroup. Well, then it's, by the virtue of the fact that this is an abelian group, we know that GHG inverse equals H for any H in H. Because this is just a way of writing GH equals HG. And so GHG inverse is the same as H, and H is normal. So the problem with being a normal subgroup or not is a property that's interesting for non-abelian groups. For abelian groups, there's nothing new when we talk about normal subgroups. But let's look at a non-abelian group. So that if we look at the dihedral group, it has a subgroup consisting of the rotation. So remember that, just to be completely clear, that Dn consists of the identity, the rotation, rotation squared, up to rotation to the n minus 1, and then there's a reflection, SR, up to SR to the n minus 1, and the property is that SRS equals R inverse. And that's enough to compute in the dihedral group. If we take the group of rotations, the claim is that this is normal. And to check that, we need to check, first of all, that if we take a power R to the I times H, what is that coset? Well, we multiply every element of H by R to the I, and we get R to the I plus 1, R to the I plus n minus 1, but this is just H again. Sorry, this is, just H again. And the right coset, similarly, HR to the I is also H. And that shouldn't be a surprise, because we already know that if you take a coset of a group, and you multiply, you consider the coset corresponding to an element of the subgroup, it's the same thing. And so the only other things we have to check is the element S. Because if we look at SR to the IH, this is the same as SH. And that consists of S, SR, out to SR to the n minus 1. But what about H, SR to the I? That would be the other coset. By the way, yeah, so this is, on the one hand, first of all, it's going to be S, RS, R to the n minus 1 S, R to the I. And now we can use this property to move our S's all the way past all the R's. So we would have S, SR inverse, SR to the n minus, to the 1 minus n, R to the I. This is just SH again. Because if we are looking at the rotations, if you have the set of rotations this way and the set of rotations that way, they come to the same thing in the end. So this is SHR to the I, but we already showed that HR to the I is H, so this is SH. So there are only two cosets, and that's not that shouldn't shock us, because there's dn has 2n elements and H has n elements, so the number of cosets is 2. And there's 2 left cosets and 2 right cosets, and they're the same. One of them is H, and one of them is SH. And therefore, this group is a normal subgroup in the dihedral group. And then let's look at an example which is not a normal subgroup. So let's take S3, and let's take H to be the subgroup consisting of the identity and the element 1, 2. So here the index, the number of cosets, is 6 divided by 2 is 3. So there are 3 left cosets and 3 right cosets. So what are the 3 left cosets? Well, let's do the left ones here. We have H, and then we have the rotation times H, which consists of 1, 2, 3, and then 1, 2, 3 times 1, 2. So let's work that out. It's 1 goes to 2 goes to 3, and then 3 goes to 1. And then the other coset we can get by taking 1, 3, 2 times H, which is 1, 3, 2, and then 1 goes to 2 and 2 goes to 1, 2 goes to 1 and 1 goes to 3. So those are our 3 left cosets for H. We did this back when we were talking about Lagrange's theorem and working with cosets. If we want to do the right cosets, then on the one hand we again have H, and then we have H times 1, 2, 3, which is 1, 2, 3, and now we have to do not 1, 2, 3 times 1, 2, but 1, 2 times 1, 2, 3. Here we have 1 goes to 2 goes to 1, 2 goes to 3, 3 goes to 1 goes to 2. And we have H times 1, 3, 2, which is 1, 3, 2, 1, 3. And now you see the left and right cosets are not the same, because here, this coset, let's use a different color. This coset has 1, 2, 3, and 1, 3 together, but this has 1, 2, 3, and 2, 3 together. And this has 1, 3, 2, and 2, 3 together, and this has 1, 3, 2, and 1, 3 together. So the sets of left and right cosets are different. Basically what's happened is that in the 6 elements of the group have been divided up differently when you did the left side and the right side. And so this group is not normal. We can look at a few more examples of things which are maybe a bit more exotic. So remember that GL2R, this is the collection of matrices, 2 by 2 matrices with real entries whose determinant is not 0. And SL2R is the subgroup of matrices whose determinant is exactly equal to 1. And it's a subgroup. And I claim that it's normal. So first of all, these are both infinite groups. And as we'll see, the index is actually infinite. So what are the cosets? So if we take a matrix, let's take a G in GL2R, and let's use the GHG inverse criterion. So we have to check to see whether GHG, and this is H, this is G, is GHG inverse equal to H? Well, if H is in H, that means that H is 2 by 2 with determinant 1. What about GHG inverse? Well, that's a 2 by 2 matrix, and its determinant is equal to the determinant of G times the determinant of H times the determinant of G inverse, which is equal to the determinant of H, which is equal to 1. So because of the fact that the determinant of a product of matrices is the product of the determinants, if you multiply by GHG inverse and H has determinant 1, the determinant of G and the determinant of G inverse cancel out. So this shows that that SL2R is a normal subgroup of GL2R. The coset representatives are the possible determinants. And those are we'll have to look at this example in more detail later, but the coset representatives correspond, the possible values of the determinant of G is any real number except for 0. The possible determinants for SL2R all have determinant 1. So the coset representatives are going to turn out to be anything in G which has the same determinant is in the same coset. And we'll see that later. What about Sn and An? So remember, Sn is the symmetric group, all permutations. And An inside Sn is the subset of even permutations. And we claim that this is a normal subgroup, and to check that, the proof that An is normal is we choose G and Sn, and we choose any A in An, and we must show that GAG inverse is in An. In other words, we must show that if A is an even permutation, so is GAG inverse. And so there's two cases. If G is even, that's automatic. That's because the product of even permutations is even. And if G is odd, well, then G times A is odd because it's an odd times an even permutation. And then G times A times G inverse is even because it's an odd times an odd permutation. GA we just said is odd, and G inverse is also odd. So when you multiply odd permutations together, you get an even permutation. And so you conclude that GA, G inverse is even. So every no matter whether you do GA G inverse with G odd or G even, if A is even, it stays even, and therefore the alternating group is a normal subgroup in the symmetric group. Couple more examples. The quaternion group. So remember what the quaternion group was. It has 8 elements, and it satisfies the rule that I squared, J squared, and K squared are all equal to -1. Ij is K, Jk is I, Ki is J, and Ij is minus Ji, and Ik is minus Ki, and so on. And I guess the last one is Kj is minus Jk. So the I's and J's anti-commute, and then there's this cyclic relation among them, and you have to keep track of the signs. So the claim is that this 2-element subgroup -1, 1 is normal. And for that, we have to check that if you do, so again, we have to check, so let's let H be -1, 1. Then we have to check that GHG inverse equals H. And so here you really have to just worry about I, J, and K. So I times -1, 1 is minus I, but -1, 1 times I is also minus I. J times -1, 1 is minus J, which is the same as -1, 1 times J, and similarly for K. So there are 4 cosets, as you would expect. You have a group of order 8. You have a subgroup with 2 elements. So the number of cosets is 4. And the 4 cosets correspond to H itself, and then the one that has plus or minus I, the one that has plus or minus J, and the one that has plus or minus K. Those are the 4 cosets. And it's normal because the left cosets and the right cosets are the same. And the thing about the quaternion group and -1, 1 is that -1 and 1 are the center of the quaternion group. -1 times I is the same as I times -1, -1 times J is the same as J times -1, and so forth. And it's actually generally true that if you have a group, its center is always normal. And the reason for that is, if we consider, there's various ways to do this. Let's look at the condition. So maybe we can let's just write out the center. Suppose the center consists of E, Z1 out to ZK. And let's take a G and G. So then G times that subgroup is the coset which has G, GZ1 out to GZK. But the Z's are in the center. And the thing about the center is that they commute with everything. So this is the same as G, Z1G, ZKG, which is the same thing as Z of G, G. So the left and right cosets agree. So the center is normal.